number 4?
Oh yeah, I gotta make sure.
Right? Not number 4. Not problem number 4. I was talking about, you're talking assignment number 4, right? Or 3?
Assignment number 4 is the last one we did.
Okay.
Assignment number 5 is the one he
Yeah, I
assigned.
just
Alright.
assigned a 5.
Alright. Oh, did you assign it?
Yeah, I forgot to post that until Tuesday. I included that in the email.
Assignment is part of an unpublished module that is not available.
Really?
Yeah. So what it'll do though, if you look at our calendar, it's been there. So
Sure.
I see
You just can't see it.
Yeah, so when you click on your link to open it up, it's so it might be you might have did the date.
I just
not
forgot to
published.
publish it.
Yeah.
When does that do, man?
It says
Well-
the 27th. Oh yeah, yeah. This one I didn't write down the questions, so I didn't know if they did. I definitely didn't do that yet.
Give
me a second here.
Try one yet? I
No,
knew you tried one on the way down.
no, I didn't.
Open them bad boys up.
Yeah, they were.
Okay, so I forgot to publish assignment 5 on Tuesday when I wrote it up for you. Sorry about that.
We forgive you.
So it's
Oh shit.
kind of weak.
Might make it easier or what?
Was it? Oh man, I don't. That's. Oh.
So the first section is 3.3 A through F. And what you'll see when you look at that portion is this is part of the homework from section 4 where you drew the shear diagrams. Now you just need to draw the bending diagrams. Okay, so that'll be the first portion. Oh, sorry, which page?
3.3.
99?
Page 98.
98?
Oh, hey,
Yeah,
man.
they usually bands.
Wait, what?
And then
I have AB there.
Wait a minute. Hold on there.
Rush instantly has a problem.
and then 3.4 A through D.
Which one, Lewis? There's no problem.
What?
By the way, you can make sure.
Are you talking about?
3.4 is on 102.
3.3 A to F.
3.3 A through F is on page 98.
3.5. This is already a.
8 through O.
Yeah, so it pulls you back to those beams that you already analyzed for shear.
Sure.
Yeah, those are guys for that.
Okay.
Problem 3.2.
We're gonna go over bending diagrams again, right? Or can you?
Do you want to?
Yeah, because I got my notes here.
Yep.
But the last one we did is when,
Looking at a cantilever beam?
yeah, the ones
Yep.
that stick out.
Yep. Do you want to look at another cantilever beam or do you want to
No,
look
I'd
at
want
do you want a beam with, where you have a
like
section
a
of the
beam
beam past
with
the
like,
support?
yeah, like one of these, you know, where we got an impact or a force here, but then two.
Sure. Okay. And then I'll change the due date to next Thursday. Okay, so that it won't be due before next Tuesday. That way we can deal with questions that you may have on Tuesday. So,
Let's say 8 through O.
what's that? A through, this is a poorly drawn.
I'm gonna say, damn, how many?
Yeah, no, there's no reason to evaluate 14 different beams for bending. So,
I mean, I'm glad we're on the same page.
okay, so we'll consider a beam. And we'll go back to, we'll simply support it. And we'll look at 2 uniformly distributed loads and a point load then. So this looks to be about 100 pounds per foot. And this guy's about 300 pounds per foot to scale. And let's put 500 pounds.
Get the 8.
Yeah.
Okay, that was Cloud Bear.
Yeah.
You're excited for bigger and better things.
Okay? So,
Shit.
so we'll call this guy R1 and we'll call this guy R2, right? Be consistent. So we'll need to figure out what our equilibrium is, right? Okay, so what do we do with our uniformly distributed loads?
Come in half.
What do you mean?
Well, you take 100 times
7.5.
15, right?
7.5.
And then you put it at 7
That's 7.5 feet.
So 1,500.
Okay?
No.
Okay, and then what about our distributed load that's 300 pounds per foot?
2,400.
And John, where is it located?
Add,
4 feet from R2, right?
yeah, so 11.
Okay, everybody followed that, what we're doing? So we're resolving them into point loads by multiplying their magnitude per foot over the length that they're distributed, and then putting it at the midpoint of where they're located.
So in the point where
300 and
we-
100.
Yeah, sorry. That looks a little bit better.
Yeah.
Actually, it looks like 100.
Yeah, I can see it.
Okay. And then we know that we have our 500-pound point load. And then we have R1 and R2. Okay?
So -15.
For this beam to stay in place, right, we can't have any rotation of the beam. We have to have all our moments equal 0. So do you want to look about R1 or do you want to look about R2?
Consistent.
Look about R1. Okay? So, does R1 try and rotate about the reaction R1? It's passing, its line of action is right through that point, right? So it's not going to have any rotation. What about our 500-pound force?
Yes.
Yes.
Okay? And is it operating clockwise rotation?
Yes.
Or is it trying to counterclockwise? It's trying to operate clockwise, right? So it's a positive value. And how far away is it?
6 feet.
6 feet away. Okay. We have resolved the 100 pounds per foot uniformly distributed load as a 15-pound foot, 7.5 feet away. Okay? Guess I should have thought through those dimensions a little bit better. And then we also have a 2,400 pound foot that's 11 feet away, right? No?
Oh, yeah, because it's at 4 feet, right?
It's 4 feet from R2 and our total span is 15 feet.
Oh, okay. Good, Terry.
What about R2? Is R2 trying to rotate about R1 in this direction or in this direction?
Counter.
It's counterclockwise, right? So it's going to have a negative value.
So, just fine.
That's fine.
10.5, right?
All of it together is like 40,650. Jesus, beautiful.
Right?
Divide that by 2710. So then do we do? Okay.
Does that make sense when we were looking at this?
4,400 was 1,500, 2,400, and the 500. Right? But we just make it
I'm sorry.
positive.
Oh, yes, sorry. Yeah, so I just summed this. 'Cause remember, test equals 0, so I just added it to
Yeah.
test. So R1 equals
Okay.
the sum of all your forces in the vertical direction minus R2. Does that make sense that we need more capacity over at R2 than we do at R1? Right? We've got heavier loading structure as far as that being the setup. Okay? So now we know what our reactions are, so now we can draw our shear diagram, right? Okay, so when we just get to the right of R1, but we haven't gone an appreciable distance, what is our shear going to be?
1690.
1690. Okay,
And then for
then what is it going to do up until 6 feet?
drop 600 pounds.
It's going to drop 600 pounds over that entire distance.
Yeah. So 1,090.
And when we get just to the right of our 500-pound force, what is it going to do?
Drop to 590.
Okay? Then what is it going to do for the next foot?
Drop 100.
It's going to drop 100, right? Then what does it do?
Drop.
Drops
Then it drops 400, right?
400.
Yep, because we're still dropping 100, but then we also have our 300 pounds, okay? Okay. And what is our magnitude going to be here?
negative 27.
Negative 2710, right? Scale got a little messed up. So it didn't quite plot that slope correctly, right?
So
So what else do we need to determine on our shear diagram?
that's shear.
What's that?
Maximum shear?
And we know our maximum shear, right? That's always going
Zero.
to, that's going to be occurring at, in these simply supported beams, it's going to occur at our greatest reaction. What else do we need to?
When it crosses zero.
When it's hitting 0, okay? And how could we do that? You go from either the left or the right.
Yeah, you can figure
Right.
out that triangle to the right. Couldn't you? Or do you got to figure out the angle first?
What do you want to do with the triangle?
Well, if you can figure out the base, you can see how long it is.
Okay. So how would you like to do that?
I have no idea.
So if you know that it's 2710 here,
Mhm.
right?
Yeah. And it's
And
zero.
how much is it changing?
400.
400 pounds, right? So could we say that V would equal 0? I shouldn't say F. When 400x equals 2710?
Yeah.
Does that make sense to everyone? Now we have to keep in mind that if this is what we're using, that distance is going to be measured from R2 to the point where shear equals 0, right? If you wanted to do it from left to right, how would you have to rewrite it? We wouldn't be able to use 2710. What would we have to use?
16.
1690.
I'd be careful.
You go from 490, wouldn't you?
We go from 490, okay? So this is from R2, if we're going from R1 or from the left. Okay,
So 6.78, or just 7, I guess you call it.
yeah, it's not quite gonna be 7, right? Because
Yeah.
it'd have to be 2,800 for it to be equal
I
to,
got 6.775.
yeah, that sounds, we'll just call it 6.75 feet to make the math a little easier.
So where are you getting the 400?
And this will be about,
Cause that's the
400
dropping,
feet.
400 feet.
The 300 and the
400
100.
pounds per foot.
So you have 300 and 100, so it's 400 pounds a foot that you move towards the zero.
yep, so all we're doing, Jay, to determine is, we can start at this point, or we can start at this point and change 400 pounds per feet. And when that equals 0, that's gonna tell us when our shear equals 0. Okay? And remember that if we didn't have these uniformly distributed loads, we wouldn't need to determine this, right? If we just have point loads. So remember, if we have a point load, our shear diagram is looking something like this,
But,
right? Those different boxes. Okay?
so now that we know that, can we use Pythagorean theorem, or how does that work out when you got pounds there?
Figuring, what do you want to figure?
Well, don't we know, we need to know the length of 0 on the baseline. We just figured out the hypotenuse of that triangle.
No, we figured
Figure
out
where it
this
crosses the
distance,
zero line.
right? So, let's wait there, because that's a good question. Where is this equal to 490?
It's at 15 feet. No, it's at 7
Mhm.
feet.
That's 7 feet, right?
Yeah.
So if we
7
add
feet.
on our 1.25
Oh.
feet, V equals 0 at 8.25 feet
From our one.
from R1.
Okay.
Or 7.75 feet from.
Or if
Or
it's 6.75 feet,
feet.
Yeah, yeah, yeah. Fine.
Okay, yeah. That's what I was saying.
now, what does those add up to?
15.
15 feet. So we cover our span. So we're saying that regardless of which side we're looking at it, it's occurring at the same place. So what we could use, Rush, if you want, is we could calculate the area of this
You
triangle.
know what, I was thinking, when we were using the 400, I wasn't thinking the wrong thing, so.
That's what-
But is that so I keep going to the triangle to figure out where across 0, is there another way, or is that how we do it?
That's what
Go to
we
the
did.
triangle, what do you mean?
We've used
Because every time you're like, hey, where do we cross 0, I always just look for the triangle.
Sure,
Okay.
yep, yep.
I just didn't know if I was going out.
Yeah, I think because this is also a triangle, right?
Yeah,
If we drop that down, it's got magnitude 490, and this length is 1.25 feet,
okay,
okay?
yeah.
So, when we go to draw our bending diagram, where is one place that we know we have to calculate our value of bending?
What it crosses.
8.25.
Right here, right? Yeah. At x equals 8.25 if we're going left to right, or at x equals 6.75 feet if we're going right to left. Because remember, where the shear equals 0 is going to give us our maximum bending, okay? So, is everybody good if I make this part go away about determining the reactions to do our bending diagram?
Yep. Well, that part I got, I'm saying the bending. I'm trying-
Okay, so what point should we look at? What do we know it's gonna be at the reactions?
0.
It's gonna be 0 at the reactions, right? But we need to figure out what's going on in between. So we already know that we need to figure out what's going on here, right? What is our bending at, at x equals 6.75 feet? And what is the process? Do we remember what the process is for determining bending? What's different about bending than about shear?
You gotta pass the point load.
We have to what?
Well, you gotta pass the point load.
So yeah, so remember in shear, we have to look at the left and the right-hand side of our point loads. Okay? We don't have to do that in shear, or in bending, excuse me. We just march along, okay? So at x equals 6.75 feet, so, let's see, no, we should do 8.25 to be
8.25.
consistent, right? Okay, so at 8.25 feet, what do we have acting? What's trying to rotate about that point? We're looking left to right, Okay.
1300. You got the weight
No, it'd be
times 8 feet.
the weight, yeah. it'd
Weight
be-
times 8 feet. Time.
the weight, the reaction?
Yeah.
Yep, R1
So
times 8.25 feet. I guess maybe I shouldn't have erased that, because it is,
1690.
oh yeah, 1690 right here. Okay,
500 times 8.25.
now we have to be careful. How far away is this 500-pound force from this point?
6 point, that's 8.25.
2.25.
Yeah, 2.25.
Why do you think it's 2.25, Kurt?
Because that's where the
Coming to the left.
0 is from.
Yep, it's 1 foot from here to the start of our 300 pounds per foot, and then from here to the point where shear equals 0 is 1.25 feet. Okay, so we want our 500-pound force
Negative.
to be multiplied by 2.25 feet. And John says that it's negative because it's causing counterclockwise rotation, right? If we grab onto this point, the 500-pound point load wants to rotate this direction. Okay? Very good. What else do we need to take into account?
100 and 300.
Our 100 pounds per foot,
Who are you talking to right
So it's bending.
what's that? We're determining the magnitude of our bending moment. We're at the
now?
point where
Okay,
shear
we're still
equals
at that
0.
one moment.
Yep.
Okay.
Yep, we're at x equals 8.25 feet.
Times 0.75.
Times, what do you want to do?
0.75.
Why do you want to use 0.75?
That's the distance from V equals 0. Or do you not make those as point loads?
You make them into point loads,
Okay.
but how much interaction does the 100 pound? Are you thinking of the 300 pound per foot? Does the 100 pound per foot operate over the entire span of the beam?
Yes.
So
So
regardless
when we
of
go to
where we
2
examine it, we have to include the entire portion of the 100 pounds per foot, right?
600?
So we'd have to multiply this by 8.25 feet to resolve it into a point load, right? And where is it located?
Halfway.
Halfway between where we're analyzing in R1,
So
right?
4.12.
125.
Yeah. I just let your calculator.
Oh,
Handle
you
that
don't got that one?
Well, it's 4.125, but. Now, is this rotating clockwise or is it rotating counterclockwise? about this point. Counterclockwise, right? So it's gonna be a negative value. Okay? Okay, so now Kurt, the 300 pounds per foot. How far away? Or how many feet is it acting on?
1.25?
1.25, right? Because it picks up when we have a shear value of 490 and operates all the way across,
Okay.
right?
So is that the 6? Oh, we're just doing it left of. Okay.
Sorry?
Because we're just doing that little portion of the 300 left of.
Just doing the portion of it that's left of where we're analyzing. Yep. Was your question, Steve?
So you get 300 pounds at that distance to the left, but then you use the 100 pounds the whole distance, correct?
Because the 100 pounds goes that whole
Yep.
6 feet.
But no, is the 300 on top of the 100, so you got 400 pounds there, or is it 300?
You would have 400 pounds per foot, starting here.
Okay, I missed that part.
Yep. 100 pounds per foot from this portion, acting over the entirety of the beam,
Yeah.
and then a 300 pound per foot.
What the hell is happening? What's that? 162?
0.625.
Yeah.
Okay?
Son of a bitch.
So anybody crunch the numbers? Otherwise we could just determine this.
Working on it right now.
So we're just looking to the left of that point, right?
Yep.
Okay, that clears a lot.
Yep. Yeah, you don't have to consider anything to the right of that point.
Alright.
Just like you would do with the shear. You either march right to left or you march left to right.
Do you have to like do that after this problem? You have to go to the right of that at all?
No.
Or is this it?
I got it.
You'll get the same magnitude, they'll just be acting in the opposite direction.
Okay, so
Right?
it'll be
Because
a
you're
negative.
going to be performing the same analysis, you're just going in different directions. So your negatives will become positives, your positives will become negatives.
Okay.
I got 9180.
9180?
I don't know if that's right.
Hold on.
Yeah, I don't trust you.
Yeah. You might.
How can we check it?
Find the area.
We find the area of this triangle, right?
Yeah.
So
I'm still plugging numbers in my phone.
1/2 times, what did you say it was? R2, 6.75 feet. Times 2,710 pounds.
So, no.
So if you punch that in, well, remember you gotta multiply that by half. So I mean, that becomes 1355.
That was
Times 6, it's gonna be pretty close.
I got 9,146.
It's just rounding, right?
Yeah. 2.25.
Alright. $91.80?
Yeah, I got 9180.
Yeah, that's what we'll get here, right?
That's what we're figuring for, right?
Yep.
That.
Okay, so, but that tells us our maximum.
Yeah.
We need a couple other points so we know what this thing is gonna look like, right?
That's crazy.
I think we're good there.
Yeah, I mean, that's on there. Wing it.
So at x equals 3,
Always.
what would we have? So now we're gonna be 3 feet away. Okay, and remember, we're going left to right.
Yeah, reaction 1.
69 times 3.
100 times 3. Divide by, or, and then times the 1.25.
Tapping.
Right?
Yeah.
Is it rotating positive or is it rotating negative? Is it trying to
Negative?
push it, yep, it's trying to make a counterclockwise reaction, right? So it's 4,500. So 570 pound-feet.
Drive off the cliff. Yes.
Maybe look at, how about an x equals 7.5 feet? Let's see what's going on.
Wait, what'd you get?
No, sorry, x equals 7 feet. What's that? 570?
What'd you get?
4620.
That's not.
What'd you get?
4620.
Oh,
That's what I got.
yeah. I don't know what, sorry. That's 300 pounds, right?
Yeah, and then times the.
So that should be
1.5.
4,500? So 4620, sorry.
Who laughed at me?
We all did.
Thank you.
In 30 seconds, you're tapping out. So.
Yeah, I know, right?
Supposed to know you had the right answer.
Okay, so what about at x equals 7?
X equals 7. So you do,
Reaction times 7.
Reaction times 7 feet, yep.
then the 100
Yeah, well, I got one
times
piece of paper.
7 times 4.5.
Give me one piece of paper, I don't wanna use it all. I'll give you another one.
Wait, where's that 7 feet? Is that where 300,
It's where your 300 pounds per foot starts picking up.
but would we count that there, or?
Is it trying to rotate at that point when we're looking from left to right? It's just starting, right?
Yeah, so that we don't
So
go past it.
any portion that we tried to resolve would pass right through that point.
Right through the, okay.
And if a force has its line of action through a point, it's not causing any rotation, okay? So, no, it's a good question, but you don't at that point need to take into account the 300 pounds per foot.
So, okay.
Is there anything else we need to take into account at that point?
500.
We have to take into account the 500 pound force, right?
And that's at, what was that, 6 feet?
That's located 6 feet from reaction 1, yep, so how far away is it?
120.
1 foot away, right? Is it trying to rotate, this way? Or is it trying to rotate this way?
Negative.
So it's doing
Negative.
counterclockwise rotation, right? Yep.
Hmm? I got something. 8,880. Mm-hmm.
8950?
8880.
8880?
Yeah.
I'll
I
give
think
you-
that's
you're-
right. I
you're
think
using
it's right.
calculator. I'm just trying to add it up in my head, so.
I trust what you did. That's a lot of button pushing.
700 times 3.5, that's 21, shouldn't that be 2450?
That's what you do. Let me look at this. 16 times 7.
I'm pretty sure I got 500 times 1, correct? Hopefully.
I can check for you.
I don't think we need to check it, but maybe we do. Okay, what's 1690 times 7?
You know, I know what it is.
I could have very well messed that up.
11:8, 8:30.
830, that would do it. Okay.
Yeah, there you go.
Okay, so it's 7.
I keep getting
8880,
Yeah.
okay? And then let's look at one more point. Let's look at x equals 12. So what do we have there? So now we're gonna be 12 feet away.
So. Okay. 1690 times 12.
1690 times 12, yep.
And do the 100 feet. What else is there? And 300 starts at 7 feet?
300 starts at 7 feet, yep.
Oh, we gotta do 500.
How far away?
So that comes at 6.
Yep.
6.
6 feet away, yep.
And we're at 12, so it's 300 times 5 then?
Right?
Oh, yeah.
3,000, 3,750, 7,200. If I put 12 in there, huh? So it's 16,900 plus 3,380. 20,000.
6330.
And
6330.
How's this?
Well, you can't.
So 20,280 minus 13,950? So you get
Yeah,
what?
6,330 is what I got.
330?
That's it, I'm drawing my bubble.
Okay. So it'll look something like that. So questions on constructing these moment diagrams?
That was still that first question I asked you about, right?
Yep.
Alright.
But keep in mind, the first set of homework, you already have the shear diagrams, right? So it's just transforming those shears into bending diagrams. And we won't typically have to, you won't typically have to determine the reactions for you. Okay? So this is what we're after here. Okay? And it's not that you necessarily have to calculate it at 5 points. Okay? Just determine it from, if you're dealing with something like this, if you're dealing with a lot of uniformly distributed loads, probably just need 3 points.
Okay.
It's gonna be, it'll be some sort of parabolic curve. Okay?
Okay.
And then keep in mind that if you're dealing with point loads, then your bending moment curve will be straight lines. Okay? So, all right. So that homework seem achievable? Seem reasonable for next Thursday?
Yeah, I'm sure we'll have questions on Tuesday.
That's fine.
We don't have class on Tuesday.
That's the whole purpose of.
Why don't we have class on
You don't have
Tuesday?
class on Tuesday?
Why do we have class on
Is
Tuesday?
it there the career fair next?
That's on
That's Wednesday.
Wednesday?
Career fair's on Wednesday. It's a good try though.
You gotta be more
I
positive
appreciate
when you're
the
trying to
effort.
sell that.
What's that?
You gotta be more positive when you're trying to sell it.
Yeah.
Don't say hesitate.
I don't know what's better, Travis.
Okay. So, well,
I know what I'm doing.
do you feel good on bending? Should we work on one more problem before we move on to chapter 4? Or do we want to move on to chapter 4?
I don't wanna do either.
Well, we gotta do one or the other. We have too much time.
Either or.
Go investigate those chicken nuggets.
And chicken nuggets aren't on the agenda right now either. We ready to move on to chapter 4?
Might as well.
Got it.
Get into it.
Let's just do it.
So, beginning in chapter 4, we look at no longer just using all of these force equations to figure out random things that are going on. Now we actually want to start talking about the materials, what's important about them, what we need to know in order to start determining how we size these things. Okay, so what chapter 4 goes into is kind of this structural system. So they talk about 3 basic types of systems, and it certainly isn't all-encompassing. But if we understand these, we should be able to grasp pretty much anything that gets thrown at us. Okay, so what we look at is we look at shear walls, we look at a braced frame, and we look at a moment frame. And at this point, we aren't going to do very much with any of the 3 of these, at least with respect to chapter 4. We're just going to look at kind of how we generally look at a preliminary sizing out for a building, whether we're looking at 1, 2-story, or 4-story, or 10-story, kind of moving on throughout it. When we think about a shear wall, what does a shear wall mean to you? What is its purpose?
A wall
Prevent
that will stop.
lateral movement.
Yeah, it's absorbing lateral loading, right? And so when we talk about lateral loading, what's the big thing that we need to consider with
The
lateral
wind.
loading? What's that?
The wind.
Wind load, right? Okay. If we lived out in California, what would be another thing?
Earthquake.
It'd be seismic, right? Yep. Okay. And the one thing, while we don't have to worry about seismic loads, a portion of the wind load for us could be from the effects of a tornado, right? But that would still fall under the wind load. Okay, so I forget. Oh, it was Hadorf last semester who brought up
Oh, don't bring that up.
the World Trade Center bombing, right?
Paying for this.
So, but we have to be mindful now that with some structures in the government sector, we may have to take into account things like explosions, right? Or impacts.
Controlled demolition.
Yep. Okay, so it's an unfortunate side of the times that we live in. What about a braced frame? How's our braced frame going to be different than our shear wall?
Got braces.
Yep. Maybe we're dealing with
Cross breeze.
diagonal bracing, some sort of cross bracing. We're going to be doing some sort of eccentric bracing, right? Okay, so here's, again, we're absorbing lateral loading. One point of issue with our bracing, and this gets back to our truss analysis, is we have to be careful with our members in compression. And what we're interested in is what's happening for buckling of those compression members. Do you remember what buckling is? We haven't done really any homework problems with them, but I've had you read a couple little sections. One in the axial load, and then a portion of chapter 3. on shear and bending, talks about buckling. What is buckling going to do to our cross bracing?
Is that when it goes like this?
That's when it's, yep, and yeah, as Terry said, it's gonna try and blow them out, right? So it's gonna start deflecting like this, and it's gonna get to a point where the material itself will actually fail. Okay, so typically some sort of shear, bending, or combination of shear and bending to cause that failure. Okay? So that's what we're interested there. As opposed to our brace frame, what about our moment frame?
That's
Yep. So also a system.
vertical.
Absorbs lateral load, and what it actually does is we allow the frame, oops, it's a little too much comedic exaggeration. Okay? So we allow our material to have enough ductility that it's able to do a little bit of bending to help absorb that frame. Okay? The idea to keep in mind is as we're moving down through these systems, the stiffness of our structural material is decreasing. Okay? Remember that stiffness is that the ability of the material to resist a load being put on. All right? Now, it's not going to be real common that you're going to be able to get away with just using one of these types of systems. So we need to be careful in the planning and the design process of what some issues could be. And so what happens if we have,
I figured you did.
You looking it over? You didn't send it.
what happens if we were to have stiffer faces on one side of the building than the other? What could we get in, what problem could we create for ourselves? We probably won't have failure. So if we have a shear wall on one side of our building, but we're using a moment frame on the other side, okay? Probably won't have failure of the system itself, but
Be a lot of movement and be loose on one side.
you could have cracks, right?
Separation.
Yep, we could get into issues with our interior finishes. We could get into issues of if we have to separate material types, we could have problems with our expansion joints. Okay, so it gets back to that age-old problem of as these buildings are moving at different rates, what's going on with them? Okay, if we're making this out of CMU, maybe we're cracking the joints, right? If we're dealing with a timber frame or a wood frame, and we've got sheetrock in there, we're maybe cracking our sheetrock. Okay, so probably not getting us into a huge structural issues, but it's going to certainly going to give us problems from an aesthetic standpoint. Still leads to a pissed off owner, right? Which is what we try to avoid. Okay. They also talk about mixing systems, but that's the same thing as that. What about geometric irregularities? So what happens if we're using a shear wall on both sides of our building, but our building isn't a perfect square? Because engineers don't design buildings, architects typically design buildings, right? Architects don't like perfect boxes. Engineers designed all the buildings, everything would just be a box because it'd be real easy. But if we have a shear wall here, and we have a shear wall here, what could potentially create an issue?
Bigger.
This wall right here. or something?
You have greater distance, so you could potentially get greater deflection here than you would here, right? So you could have some sort of issue, potentially in your foundation, potentially in the wall itself. So that's something that we need to keep in mind with when we're talking about stiffness in our buildings. What's going on with the total footprint of the building, and how is this going to interact with it? Okay. So does that make sense? What's kind of going on? And that's kind of at that 30,000 foot level. I don't think that there's anything too crazy going on here, but that's kind of their introduction to the structural systems. We go into a little bit more detail with the shear wall versus a brace frame versus a moment frame, and then we get into talking about how we use them specifically with each of the material types. Okay, so.
Mark, did you get that now?
Yeah. What?
Are you reviewing now?
No, I have. I'm just going over it again. Huh? I don't do no cards.
So we haven't tried to look at a shear wall and how to analyze it at this point this semester. But what have we been looking at that we could try and model it as? We've been spending a lot of time looking at beams, right?
Okay.
So couldn't we just think of a shear wall as a very large, very deep beam? And so now we can take it, instead of it being this goofy line that I draw up on the board over and over and over, and I pin it on one side and put a roller support, couldn't we do that with our shear wall? Tip it up on its side and give it dimension into and out of the board and analyze it in the same way?
Yeah.
Okay? So that's what we've been setting up for, is to take this simple analysis that we've been doing all semester and start applying it to these 3D structures. Okay? And then, so our shear walls are set into our roofs and flooring systems. Okay? And so these systems are going to act as a diaphragm. Oops. The terminology that the book uses and that architects like to use. Okay, so the diaphragm will pick up the load. It's going to transmit it into our shear wall, or if we're using brace frames, or if we're using moment frames. Okay, so that's how we're transmitting these things. Then the walls and the portions of the frames take up that load. They transmit it into our columns. The columns push it down into the foundations push it into the earth. Okay, so this is all stuff that we've talked about in the past, not necessarily in this class up until this point, though. Okay, so we want to be mindful of controlling our ratios. So for our diaphragm, we want to be about 1 to 3 width to length ratio. Okay? If we start exceeding that, then we're going to want to look at some sort of intermediate system. Okay? Whether it be another system of shear walls, whether it be another system of brace frame, moment frame, whatever it is that we're doing. Okay? We want to control that same way with our shear wall height to length. Yep. I should say length to height to keep the ratios in the same proportion. Okay. If we start exceeding this for our shear walls, then we maybe want to move to a little less stiff system. And we want to maybe start looking at doing some sort of bracing, or maybe switching to a moment frame. Okay. Okay, so we talked about buckling in a braced frame. Keep in mind too, with our braced frame, do we necessarily just have to do this in our walls? Can we also brace our flooring systems?
Yeah.
Okay. So if we can treat these as large, deep beams, And then we can look at bracing them, right? Isn't that what we did with the trusses? Isn't that all a truss is when we're doing truss analysis? We can then turn it into a large, deep beam, and now we can start doing analysis on that way as well. Okay, so you can use all those skills that you used in analyzing trusses to help you with either a braced frame wall or in a roofing system, a floor joist system, anything of that nature. Okay? So, and then our moment frames, what's key for our moment is we allow our members to move. But we keep our connections rigid. Okay? By allowing the members to be able to move, they're able to absorb that energy, they're able to deflect a little bit, but keeping those connections in place, because again, keep in mind, we're talking about very small deflections, okay? Won't interfere with our structural system. Think back to the Boy Scouts of America building that we went to last semester. Remember when they talked about the CEO's office that they have? They were doing brace frames in that bay where that office was going to be. And because of his window, they were no longer able to brace frame. They had to switch to a moment frame for that portion. Okay, so we can mix and match any of these three depending on what it is that we're going to do. Okay, so the moment frame from a design standpoint, even though it's not as stiff, stiffness decreases, right? Except no one can read stiffness. Okay. Even though our stiffness is decreasing, we get a little bit more flexibility in our moment frame, right? We don't have any bracing that we need to worry about. Okay? If we need to cut out a window, we don't have to worry about structural integrity of our shear wall. Okay, so it gives us a little bit more flexibility. We should say two. Because of this bending though, we're typically going to require larger members. Okay. Any questions on those three major types? Whether it's the shear wall, the brace frame, or the moment frame? Okay. So after we look at these portions, then they move into the different construction types. And there's a handful of example problems. And we'll probably just be able to look at the wood example problem today, which is fine, since you already have the bending homework to be doing. We can look at the steel and concrete on Tuesday. So the example that we're given is determine a preliminary design for a house. And before we draw it up, I want to point you to a couple specific tables in the book that you're going to need. So page 168 and 169. Has span distances for joists. And depths for wood beams.